Hello everyone, my name is Hannah Collins, and during this presentation I will talk about one of my PhD projects and the project I focused on in this class about data analysis and visualization in R. The name of the project is Geospatial Patterns of Per- and Polyfluoroalkyl Substances in Arizona Waters Inform Sustainable and Equitable Water Management. So first of all, what are per- and polyfluoroalkyl substances, for which the acronym is PFAS or PFAS? Well, PFAS are a group of more than 14,700 man-made forever chemicals. They are persistent, mobile, and toxic substances increasingly detected across the United States waters. They are incredibly stable and difficult to break down and detoxify because their chemical structures consist of carbon-fluorine, or CF bonds, as you can see here. The CF bond is the strongest single bond in organic chemistry. Because of the stability and thus the persistence of PFAS, understanding their distribution in the environment is crucial for protecting public health. One of the largest contributors to PFAS contamination in the environment is aqueous film-forming foam, or AFFF, historically used in firefighting since PFAS is very good at extinguishing fires because of how thermally stable they are. AFFF was used at airports, military bases, and industrial sites, and has created long-lasting groundwater plumes because the foam can seep underground and contaminate groundwater after it is used to put out fires at sites. These plumes can migrate far from the source, creating regional groundwater contamination challenges. Arizona is particularly vulnerable to PFAS because the state relies heavily on groundwater, which makes up about 41% of its drinking water supply. Groundwater and reclaimed water are both susceptible to PFAS accumulation. As Arizona continues to grow rapidly, continued reliance on these water sources increases the urgency to understand and manage PFAS risks. With significant industrial and population growth, such as expanding semiconductor manufacturing, which involves using PFAS to create microelectronics, Arizona's dependence on groundwater will likely become even greater due to both decreasing water quality and water quantity. This trend emphasizes the need for early detection and risk assessment of contaminants like PFAS so that the state can sustainably manage its water resources. Although the Arizona Department of Environmental Quality, or ADEQ, which is a state government agency, has collected over 6,000 PFAS samples, the state lacks an integrated hazard index system to interpret the potential health implications of these data. Without such a framework, it is difficult for regulators and utilities to prioritize sites, communicate risks, or plan treatment effectively. This brings me to the objective of my project, which is to generate 3 hazard index heat maps for PFAS in Arizona's drinking water and groundwater sources, which I will discuss in the following slides. To interpret the 3 different hazard indices, several key acronyms are important to keep in mind. A hazard index, or HI, is the concentration of a PFAS detected in water divided by its health-based benchmark value, or HBB. If the HI of a PFAS is greater than 1, that means it is either unsafe to drink the water that the PFAS was detected in, or that the public water system the PFAS was measured in is in violation of federal law. There are 2 different types of HBBs. First is health-based value, and second is the Environmental Protection Agency's maximum contaminant level, or MCL. These definitions help translate raw concentrations into meaningful indicators of potential health risk. To create the first HI, I worked with the EPA's existing PFAS HI for 4 of the 6 currently regulated PFAS. This formula serves as the foundation for extending hazard calculations to the newer 6 PFAS regulatory framework. The 6 United States federally regulated PFAS for HI6 are PFOA, PFOS, PFHXS, PFNA, PFBS, and GenX, all of which are acronyms for long chemical names, such as perfluorooctanoic acid for PFOA. An HI6 value above 1 suggests a potential exceedance of regulatory limits when these PFAS are considered collectively. This provides a clearer picture of regulated PFAS burden at each site. This slide shows the regulatory thresholds used to calculate HI6. Basically, they are the MCLs provided by the EPA for the 6 PFAS. This HI6 heat map was created by calculating the HI6 at each site across Arizona where PFAS was measured in water between 2013 and now, and plotting all the data using R. This heat map reveals spatial patterns of federally regulated PFAS in Arizona. The highest HI6 values are located at these three locations in orange, which is a strong indicator that these locations should be prioritized in regards to treatment and subsequent monitoring. For each location or point on the map, the inner circle is the highest HI calculated at the location, and the outer circle is the lowest HI calculated at the location. HI sum is a cumulative index representing the total PFAS burden regardless of regulatory status. It sums all PFAS concentrations detectable at a site and normalizes them to a conservative health-based benchmark for all PFAS detected in United States waters. This metric captures risks from emerging or unregulated PFAS that HI6 does not include. This map shows that no locations stand out compared to the rest in terms of overall total PFAS burden. HI Max is the most conservative hazard index used in this project. It incorporates health-based benchmark values for 32 PFAS compounds, summing their individual hazard ratios. This index is especially useful for identifying risk from PFAS that lack federal regulation but have published health-based values based on risk assessment in the literature. This slide shows the health-based values used to calculate HI Max. 6 of these values highlighted here at the top in yellow are the EPA MCLs, while the remaining 26 are derived from nationwide health benchmarks compiled by the Interstate Technology Regulatory Council, or ITRC. These values allow HI Max to incorporate a broader range of PFAS into hazard assessment. HI Max map reveals multi-compound PFAS hotspots across the state, particularly near industrial corridors. This visualization captures sites where unregulated PFAS dominate hazard scores. It broadens the perspective beyond regulated compounds to include those with emerging toxicological concern. This comparative figure displays all three heat maps simultaneously. It is evident that the results are similar for HI6 and HI Max, and that the sparse locations with the highest HIs should be investigated first, especially for HI Max. The HI sum map is promising for Arizona in that the overall PFAS concentrations at all the sites do not greatly exceed the health-based benchmark for the sum of PFAS, which again in the United States is 70 parts per trillion. This visualization shows the spatial distribution of sampling locations statewide and shows where PFAS were and were not detected, and shows locations where PFAS should be monitored to fill monitoring gaps, such as in the northeast corner of the state, or other blank areas on the map, and locations where PFAS need to be removed from water sources if they have not been already. Basically, everywhere where PFAS has been detected, especially in larger amounts based on the heat maps I showed previously. This bar chart shows how frequently each PFAS compound was detected. Compounds such as PFOA, PFOS, PFHXS, and PFBS, all of which are federally regulated PFAS, appear most often, reflecting their widespread historical use and persistence, and also monitoring technologies. These detection patterns help contextualize the hazard index results. NAs show instances for which PFAS were not detected. This figure shows the distribution of the concentrations for all PFAS compounds detected in Arizona, with box plots summarizing each compound's median, variability, and outliers. Several compounds, particularly PFOS, PFHXS, and PFBS, all three of which, again, are regulated PFAS by the EPA, display wide concentration ranges, including high outliers exceeding 600 parts per trillion. These patterns help identify which PFAS most strongly influence hazard index values and highlight compounds that may require targeted monitoring or treatment. Now that I have shown you all the data and am about to conclude the presentation, I just wanted to revisit the title of the project and particularly emphasize the part about informing sustainable and equitable water management. This leads me to the conclusion that this work, with some more fine-tuning, could transform Arizona's PFAS data into actionable hazard index maps, support regulators and utilities in understanding risk, and guide prioritized sampling and treatment decision-making. These visual tools can also enhance public communication by making complex data easier to interpret. Finally, I want to acknowledge the collaborators, faculty, and mentors who supported this work. Their guidance helped shape the development and interpretation of these visualizations. Thank you for your time and attention, and I hope that this was informative.